Okay, what we're going to finish up that chapter 2 with is reducing radicals, because we need to be able to simplify with the exact values and not think that we have to go to decimal. Because decimal on a lot of square roots is approximated because you have to round it. That's not an exact value anymore if you round it. So we're going to go through simplifying so that we will keep our expressions or answers exactly right rather than approximating them. Okay? So I still see some iPads that are screwed up. If we flipped over, calculators away. All right, a radical is what you call this symbol. You probably would have called it a square root symbol. Well, it can be used for more than just square roots. It can be used for cubed roots, which would be written just with a little 3 on it. Cubed root, or a fourth root, or a fifth root. You can have all kinds of roots. So that's more of a generic symbol rather than just a square root symbol. So if you don't have a number written out front, it's understood that it's a 2, but it's a square root instead. The number or expression that's underneath it is the radical sign. The radicand is under the radical symbol. So when you're doing something like square root of 16, the 16 is the radicand. So what does it mean to do the square root of a number? If I asked you the square root of 16, you would respond
4.
Why?
Because 4 times.
Explanation? You're able to explain. You want to try?
Because 4 is the only number times itself that equals 16.
Okay, so you're looking for a number times itself. 2 identical numbers that multiply to give you the 16. So what are some of the perfect square numbers that I would think you should know? Probably would know the square root of, obviously 16.
36.
4. Square root of 36.
25.
Square root of 25. Square root of 9.
144.
Square root of 81. Okay, what is the square root of 144?
12.
12. How far up do you know?
124.
Is that as far as you typically go?
Already like 20 times.
Square root of 196? 14 times 14.
Yeah.
First day. What is your first?
Okay, so there are, okay, back together. So there are perfect squares that have an integer, but then what if we do the square root of 50? All of a sudden you're going to want to grab your calculator because you don't know it, okay? We're not going to round it. Square root of 50, if we went decimal, it's bigger than the square root of 49, which is 7. So we might guess it's 7 point, maybe 1, but I don't know if that's exactly right or not. And without grabbing a calculator, we probably would be kind of stuck. What we're going to do with something like the square root of 50 is simplify it by reducing it. When you reduce a radical, we're going to try and make the radicand number as small as possible by taking out any perfect square factors that it has. So we're going to make that number as small as possible. As a result, we will get numbers out front that have been pulled out of it, basically. So we are going to simplify radicals. I think you have to fill in some blanks, maybe. We're going to try and create a radical expression where the radicand contains no perfect square factors other than 1. So how will we know when we're done that radicand can't be divided by 2 identical numbers? No perfect square. So we're going to look for duplicate factors and factor them out. I'm going to show you a method that works for whether you're doing a square root, a cube root, a fourth root. So you can probably use that as you go on to Algebra 2. Now, after we see what's going on, some of you will be able to factor out a perfect square mentally. So we'll get to that point eventually. So let's take that square root of 50 that I was mentioning. Square root of 50. I want to factor it into what all of its factors are. And this is why you did the factoring tree. Okay, so let's get it factored into primes. 50 is what times what? 2 times 25 5 is,
Five
or
times
25
five.
is
5 and
5 times 5, we're in primes right now.
Mhm.
Okay, so if I brought all those primes over, it's 2 times 5 times 5. If you write those prime numbers in order and pair them up, or write them in order, I guess we'll do that automatically. That'll make the next step easier. We're looking for identical factors, right? Okay, you see any identical factors?
5.
Yeah, the 5. So we can reduce this 5 part. Okay. Here's where I decide, okay, what should I show you? Okay, this is what you're doing mentally. Square root of 2 and square root of 25. Because you're pairing that together. What's the square root of 25? A plain old 5. Square root of 2, I really can't do anything with. So we're simplifying this to be, we usually write the whole number first so that it doesn't look like it's under the square root. 5 times the square root of 2 is a simplified version of the square root of 50. The radicand is smaller. It doesn't have any factors that are duplicates. It's just 1 times 2. There's nothing more that you could duplicate or have duplicates to factor out. Now this step in between here, some of you will need to write that, others will be able to go directly from, okay, I have a pair of 5s, so a 5 is going to come out. And then what doesn't have a partner stays under the radical. So some of you will be able to go that way. All right, let's use some of the numbers that were off of our bell ringer. Page figure, what do we have? We had 24 on the bell ringer. Is that one of the numbers? Okay, 26 we had, what would you do with the square root of 26? Because its factors were
2 and 13.
2 and 13. Partners?
No.
No, there's no pairing up. So you don't have things that can hold hands and walk outside of the square root as one. Funny way to remember it. Okay, so there's no partnering, so it just stays square root of 26. You've run into fractions that can't reduce. There are square roots that can't reduce. So that will happen sometimes. What was another one on the bell ringer?
70.
70. Okay, square root of 70. What did we get that to factor as?
275.
2 times
5.
5 times 7.
Yeah.
Partners? No. So that one, again, could not be simplified. Okay, what's something that had duplicate factors? What was the first, second number?
That was 70.
That was
Second.
70?
The third
Okay.
one's 147. And
Okay.
that has a duplicate.
All right, so from our bell ringer, square root of 147. Okay, what was our factoring on 147? 3 times 7 times 7? Okay. So 3 times 7 times 7. That one's got partners. Okay, does the 7 stay in or go out? Does it go out as a 7 or a 49? 7. So this ends up being 7 times the square root of 3. And if you can't get there directly yet, let's think what we're doing. Square root of 3 times square root of 49. Square root of 49 is a plain 7. Square root of 3 we couldn't do anything with. We write the 7 in front so you don't question whether it's under the square root or not. So it's up to you if you need that in between step. Okay. Let me scroll it back down a little bit. Okay. What was another one from the bell ringer? 100? Okay, now if I gave you the square root of 100, could you come up with it right away? Yeah, probably. Let's see if our method works for that one. What would be your prime factoring for 100?
2 times 2 times 5 times 5.
Okay, my screen's kind of going off a little bit here. I need to make it a little smaller. Okay, so that would be touch isn't quite right at the moment. Okay, we would go with square root of 2 times 2 times 5 times 5. So if we were using our current method, we're gonna pair up a 2. So what comes out?
2.
2. And there's a 5, so there's another thing that comes out. We don't have anything left for the square root. 2 times 5, 10. So the square root of 100 is 10. Our method made sense. All right, what else was there? 36? No, 32.
32, it was 32.
I think it was 32. Okay, square root of 32. So on your marker board now, look at your factoring for the square root of 32. You tell me what you think it should be. What would it simplify to be? I'm going to orient this while you're doing that. Okay, square root of 32. What would that simplify to be? You might have your factoring from the bell ringer. If not, get it factored. Not tempted to grab your calculator, are you? Okay, so pair up. There's a lot of 2s. Pair up what you can. Pair up 30 times, not 5 times.
I think it's 5 2s is what the prime factor is. Yeah. And then 2 and 8, and then 2 and 4, and then 2 and 2.
Not adding, it's actually multiplying. And I'm, on that example, I'm not sure, but it's multiplying.
I don't put factor.
All right, let's see what you come up with. Okay, you can multiply the number on the outside. Just show me your
4
board.
to the 2.
Usually written just in another order. Okay, over this side, some more boards. Still figuring it out? Still thinking over here? Should be 4 times the square root of 2. I think there were more pairs that would go out. You had 1 pair. Oh my God. I did, I absolutely did. But they should go out. Get it? Yeah. Okay, so for anyone that got stuck there, I think there were 5 2s. 2 times 2 times 2 times 2 times 2. Okay, pair up. So there's a 2 that goes out. There's another 2 that goes out. And there's a 2 that doesn't have a partner, so it has to stay. So we get 4 times the square root of 2. Now for those of you that are good at dividing and you know your perfect squares, let's see if that makes sense. If I write this as, maybe I shouldn't show it that way, but if I think of the square root of 32 as the square root of 16 times the square root of 2, what's the square root of 16? Times the square root of 2. So if you are good at factoring, you can do that type of more quickly, dividing. But the method I'm showing you works if you're looking for square roots or simplifying cube roots. You're looking for 3 of the same thing or 4 of the same thing. So when you get into Algebra 2, what I'm showing you can apply to whatever root you're trying to do. Okay, some more practice. Got that? 4 times the square root of 2? Okay. All right, let's do square root of 200. You have not factored that one yet, so you'll have to start with your factoring tree. Or if you have another method that you saw that worked. you put the square root of this whole thing. Okay, so now the pairs can come out. So this can come out as a 2. 5 choose, that can come outside.
No markers.
Yeah. Did you try both of them?
Yeah.
Okay, show me your boards. Show me your boards. Even if it's wrong, so that I know how we're doing. Yeah, you didn't get enough pairs out.
Two's not proper,
2
eight's
times
not proper.
5.
Oh, yeah.
Okay, one.
Okay, we should be getting 10 times the square root of 2.
Yeah.
Okay, and here's a couple things I saw. Can I speak, please? Okay, up here, some picked up on what I did here with the biggest perfect square. So I saw some doing the square root of 100 times the square root of 2. So that's 10 times the square root of 2. Yeah, perfect, good. If you did the complete tree factoring, let's see, you had 2 times 2 times 2 times 5 times 5. So you had a pair of 2's that comes out. You had a pair of 5's that comes out. And you have a 2 that didn't pair up. So 2 times 5, 10 times the square root of 2. 2 different methods. Some of you were talking about one as opposed to the other. Question on that before I give you another one? Okay, let's go with the square root of 72. Square root of 72, simplify, reduce that radical. Get the exact value of reduce.
Two times 2. 4 times 2 is 8. Is it 6 or 8? Why? Do you add? But you multiply. This outside, don't you? Yeah, you get 6. I did 36 right there. You have 7 2s, right? Oh! Skip all that. Yeah, copy, you're right. Okay, I know what I did.
I never did have one.
Okay, show me your boards. Show me your boards. All right. I think we're getting there. I caught a few things to talk about. Should come out to be 6 times the square root of 2 when you're done. Okay, want to see a method? If you did the complete factoring, Your factoring was 2 times 2 times 2 times 3 times 3. Pairs can be simplified out. So there's a pair of 2s, so a 2 comes out. There's a pair of 3s, so a 3 comes out. But there's a 2 that doesn't have a partner, so it has to stay inside the house, whatever you want to call it. So 6 times the square root of 2. All right, let's do one and then we'll throw some variables on it. Okay, let's go with square root of 20x squared. We'll start with that. Okay, now do the 20 just like you've been doing. And I'm going to go back to that complete factoring method. Some of you are on a different method. Now, how would you factor x squared? X times x. So if you have 2 times 2 times 5 times x, right? 20x squared factored out. So your partners, there's a pair of 2's. There's a pair of x's, which will come out as x. And there's a 5 that can't be simplified. So we get 2x times the square root of 5. Now, what if the x was to the third power?
Then there'd be an x inside the radical as well.
Okay, so then you would have an x inside the radical also. Okay. What if it were x to the fourth?
Then it would be x times 2x.
So there's another pair. Okay, back to the room there, please. Pay attention, please. Okay, so if we had another pair of x's, there's going to be another one here. So what's that going to simplify to read as? 2x squared times the square root of 5. If it's to the fifth, and we're going to have another x in here, right? Okay. What if it had a y to the second, in addition to that? So there would be a y outside. Okay. So the variable parts, just write down how many of each one there are and see what pairs up. In Algebra 2, you'll probably talk about when you do the square root of x squared, it's actually the absolute value of x instead of just x. But for what we're doing, just the little bit that we're doing, that makes sense maybe just using x. All right, let's do a couple formulas. Actually, there's 3 places that we will be reducing radicals. One of them was the Pythagorean theorem. Okay. We did some of those problems in the first chapter. Okay, let's give you a problem here. 5 is this leg, 10 is that leg. I want you to come up with the hypotenuse in exact value, reduced radical. So set it up Pythagorean theorem like you did first chapter. Leg squared plus leg squared equals hypotenuse squared. Now solve and reduce any radical answer. You have 125 equals x squared. Is that where you're at? Okay, how do you get just x then? So this was 25, this was 100. If x squared equals 125, to get x, you would be square rooting each side. And I'm ignoring the negative part because I don't want a negative for my x value. So to get x, I have to simplify the square root of 125. Factors into what?
5 and
5 and 25. 25 is
5 and 5.
5. Looks like I have 3 5s. Pairing. There's 2 5s, so what comes out? 5. So a 5 comes out, and the square root of 5 remains. So it should have been 5 times the square root of 5. That's the exact value for x. Make sense? Thumbs up or down? That one make sense? All right, no one's showing me down. So that's one place we will use with reducing radicals. Another one is the distance formula. Okay, which one's the distance formula? Write it down on your notes, probably so that you have it in your notes. Distance formula. Yep, D equals the top one. Subtract the x values and square. Subtract the y values in the same order and square. Add it together. Last thing you do is the square root. And today we're going to reduce the square root rather than go to a decimal. Okay, here are your 2 points. Let's say A is the point 6, negative 2, and B is the point 28. I want to know the distance between them reduced in radical form. You need to write x1, y1, x2, y2 to help you keep the numbers in the right places. Do you guys remember how you can tell if you can divide by certain numbers? How can you tell if you can divide it by 2?
It's
It has to
even.
be even. So any even number you can divide by 2. How about if it's divisible by 3? Now the digits add up to something you can divide by 3. So what's our number we're trying to work on? Square root of 116? Okay, square root of 116. 1 plus 1 plus 6 is 8. I can't divide 8 by 3, so you can't divide that number by 3. A 4 was, actually if the last 2 digits could be divisible by 4, then the whole thing can, because you can divide 100 by 4. So if you can do the last part. So can you divide 16 by 4?
Yeah.
Yes. So you could divide the whole thing by 4. 5, if it ends in 0 or 5. 6 was just if the dividing by 2 and dividing by 3 works. 7, I couldn't remember what that one was, if there was one. Okay. Dividing by 8, 9, those are really if it's just the smaller numbers. Dividing by 10, it ends in a 0. So maybe some of those gave you some hints. So what did this divide down into? I'm going to show some work here because I'm recording this lesson right now. 2 minus 6 squared plus 8 minus negative 2 squared. That ended up being negative 4 squared plus 10 squared. A couple people goofed that up. So 16 and 100. That's where I got the square root of 116. Okay, now let's do our dividing. What did it factor down into? 2 and 58.
2 and 29.
2 and 29. That's as far as you could go. Yeah, maybe you went, 4 and 7 is 28, right?
Yeah.
29 I think is prime. Okay, so I've got a 2, and a 29. So that simplifies to be? Is it 4 or 2? 2 times the square root of 29. Okay, I didn't see everybody's board on that one. I think I started in too much. But thumbs up or down, did you get it right or not? Get it? Okay, if not, some questions? No? Okay, got to watch our positives and negatives. So we've done the distance formula in chapter 1, but the reducing radical part on the end of it is what's different today. One more formula that we will use, and you will use more in Algebra 2. We'll use it once in a while, but probably not a lot. You used it in Algebra 1. It's called the quadratic formula. Do you recognize which one it is? Did you sing a little song or something to remember it? No? Second one down. Okay, write your quadratic formula in your notes. Okay, it's x equals the opposite of b plus and minus the square root of b squared minus 4ac all over 2a. All right, what we have to figure out is when do we use it and how do we use it? What are the a, b, and c? Okay, they come from the general form of a quadratic. And in a different color, so it stands out. A quadratic equation, not the quadratic formula, but a quadratic equation is going to have something variable squared plus something variable not squared, and then a constant. Equals 0 is the form we want it to be in. If it's not equal to 0, we have to do some adding or subtracting to get it to equal 0. Now in this form, for what we're trying to solve, the a, the b, and the c are the coefficients. So the problem is going to say solve this equation, but there will be numbers in there. My first equation we're going to solve is x squared plus 9x plus 14 equals 0. That's the one we're going to try and solve for our sample. I wrote it over there so that we could match up and figure out what's the a, the b, the c. So the a is the coefficient of the x squared, which is understood to be 1. So for the problem we're doing, a is 1. B is the coefficient of the linear term, the part that doesn't have an exponent, so 9. And the C is the constant, 14. Those are the values that we're going to use in the quadratic formula in order to figure out what x is. Okay. So I'll go back to my blue over here. So to get x, to get the solutions, we take the opposite of the b, the opposite of 9, plus and minus, because there's positive and a negative square root. 9 squared minus 4 times 1 times 14. Thank you. all divided by 2 times the A. Understand the numbers I plugged in? Okay, so let's finish going through the blue part. Opposite of 9 is just negative 9. Plus and minus square root of 81 minus 56.
4 times 4. Yeah.
No calculator, we gotta work hard here. Divided by 2.
It's really hard.
Okay, 81 minus 56. 5. Okay, so right now we have negative 9 plus and minus square root of 25 divided by 2. I need some more screen here. Okay. What's the square root of 25? 5. So, negative 9 plus and minus 5 divided by 2. Now in Algebra 2, and I'm going to let you get to the hard ones there, this might not be the square root of 25. It might be the square root of 50. So you need to reduce it, now simplify it, and then see what you can do as far as reducing the fraction some more. So I'll leave that for Algebra 2. We're just doing a little bit here. It's not all that difficult once you understand what we're doing and what you're doing there. Okay, so now I'm almost done. There's a plus and a minus, so there's 2 times I need to evaluate this, okay? So I usually draw 2 arrows. So if x is negative 9 plus 5 divided by 2, and x is negative 9 minus 5 divided by 2. Negative 9 plus 5 would be negative 4 divided by 2. Negative 2. Okay, and negative 5, or negative 9 minus 5 is negative 14 divided by 2. Negative 7. Okay, so what did we just find? What we just figured out is this green equation we had over here. If you put negative 2 in for the x, both places, and calculate, it's going to be 0. Negative 2 squared is 4 plus negative 18 plus 14, that's 0. And if you put in negative 7, both places, negative 7 squared is 49, plus 9 times negative 7 is negative 63, plus a positive 14, that should come out to be 0 also. So you're getting the solutions to the equation. All right, let's do one that has negatives in it. Okay. All right. Kind of distraction. All right, let's do one more with a negative in it. So here's the problem we're going to do. Let's do x squared minus 3x minus 4 equals 0. That's the one we're going to solve. We're going to use the quadratic formula to solve it. Remember how we picked out the a, b, c? The a is the coefficient of the squared term. What's the coefficient here? 1. So a is going to be 1. B is the coefficient of the variable term, not the squared one. So b is negative 3 because of the subtraction sign. And c is negative 4 also. We have to deal with some positives and negatives this time. So to get x, the opposite of the b, plus and minus. So we're going to come back and that's going to be a positive 3. The opposite of b, plus and minus the square root of b squared minus 4 times the a times the c. I'm going to put parentheses around the c because I don't want it to look like a subtraction sign. All divided by 2 times the a. Opposite of negative 3 is positive 3. 3 times negative 3. 9. Minus 4 times 1 times negative 4. Sounds like it's going to be minus negative 16. So that's really going to be plus positive. All divided by 2. 9 plus 16. 25. So this is going to be 3 plus and minus square root of 25 divided by 2. Square root of 25. It's plain old 5. 3 plus and minus 5 divided by 2. Now I think I'm ready to do my two parts. 3 plus 5 divided by 2 is 4. 3 minus 5 divided by 2, negative 1. So my two solutions were 4 and negative 1. Remember quadratic formula for from Algebra 1? I'm sure that you were introduced to it, probably used it to solve a few equations. So your assignment is a worksheet. And if you want to do the quadratic formula ones, they're the very last 3 problems. You want to do those first, and the other ones are easier probably. So this worksheet is your assignment. We made it through without a calculator.
I was having